My name is Nigel Bosch. Today I'm going to be talking about a couple of projects that I've been involved in where we have been trying to learn more about learning using AI methods, so it's relevant to this symposium, but specifically learning from unstructured classroom data and data that were not really collected with the analyses that we eventually did in mind during the data collection process. So I'll talk about some of the interesting challenges and findings that have come up from doing that. So the data that I'm going to be talking about today are data that were collected for human intelligence. So data that researchers collected for specific purposes like teaching evaluation. So this happens a lot actually in classrooms where teachers or institutions in classrooms, grade level classrooms will videotape teachers or the entire classroom, the students as well sometimes, to help teachers learn how to teach more effectively. And that can include practices for the teacher to help them self-evaluate, or more official kinds of evaluations. And these are not really collected with any AI kinds of methods in mind. And there are lots of other similar kinds of data. For example, videos and interviews that might be collected for microanalysis kind of research, perhaps qualitative coding of different learning phenomena, including some of the data that I'll specifically talk about today, that are also not really collected with AI applications in mind, but more with a human going over every second of the video by hand at less than real-time speed. And then things as well like course evaluations and various types of metadata or data that may come from outside the actual learning experience. There are lots and lots of different types of data like this that are collected with human evaluation in mind, even if for research purposes, not necessarily for AI research purposes. So applying AI methods to these data raises some unique kinds of challenges. So some examples are things like these types of data may not have everything that's needed for a particular AI or machine learning analysis, like they may not have labels for anything really, or perhaps just not labels for a task that is that's really something that you want to do with your AI methods. Or they may require, and often require, huge pre-processing efforts to get them into some form that's useful for applying AI methods. But there are some real benefits to doing these kinds of analyses as well. So there are things like analysis of real-world scenarios that we might otherwise ignore. If we collect data that fit into a nice box that are useful for straightforward AI, machine learning kinds of analyses, we might miss out on a lot of educational scenarios that do occur in classrooms that aren't necessarily so easily put into a structured format for a particular AI task. And we also have a benefit of when doing this kind of research of being able to get some expert advice from other domains, especially with the data that I'll talk about today, from two studies where the data were collected for qualitative analysis purposes. So then we can actually talk to the qualitative analysts and get their thoughts on these data. So the first of these projects is called Theory-Based Computational Analysis of Classroom Audiovisual Data, or TCA squared for short. And this is a project that's ongoing, NSF-funded project with a few of my collaborators here at the University of Illinois, and collaborators at Middle Tennessee State University and University of Tennessee, and some grad students and a postdoc all around. So this project team, by the way, is made up of a very kind of methodologically diverse group of researchers, including qualitative video analysts, audio analysts, and so on. So we have a lot of different perspectives on what we could actually get out of these kinds of data. So the data that I'm going to show you for this project were collected by Elizabeth Dyer, one of the co-PIs, who recorded middle and high school math classrooms some years ago to answer research questions via qualitative expert video coding. So very different from the AI kinds of tasks that I'm currently pursuing with these data. We would like to apply AI methods to explore new kinds of research questions. So especially in this case, research questions that are not really feasible to pursue with qualitative analysis because of the scale of this video data set. It has been largely unanalyzed because there are hundreds of hours of video, and it's very difficult to, time-consuming to go through that by hand at much less than real-time speed. So some of the example research questions that we're looking at from both a qualitative perspective and an AI-driven kind of perspective are things like, what ways do teachers use physical positioning to engage with groups? And among those ways, what ways are effective? And maybe how do teachers divide time between different groups? This isn't solely group-oriented work, but a lot of it is. And there's some interesting patterns with how that affects the group development and which students take leadership in a group discussion and things like that. And there's also what patterns of student movements throughout the classroom when they are moving through the classroom. How do these cluster together, and how do they relate to the different classroom activities that the students are doing, whether individual presentation or group work or individual work, and so on. So some example data from this project that I'll show you is a screenshot from some videos that were taken at the front of the classroom at different angles. So these are looking back at the students, who are not necessarily forward-facing, because these are kind of typical group work math classrooms in middle school and high school, where everybody is not necessarily seated forward watching a lecture. There are also, from this project, some videos of teacher interviews, but I'm not going to get into those in this project. So on this next slide, I'll show you a typical classroom and camera arrangement setup, and you'll see some key points, which are various points on the body that have been tracked via the OpenPose computer vision software from Carnegie Mellon. So in this screenshot, we can see key points detected. You can see the skeleton outline of most of the students in the classroom. The individual in the very back of the classroom is actually a researcher there to observe and record the videos, and someone standing near the front of the classroom, kind of leaning over the table, is the instructor. And we are, some of the research that we're interested in this data set is looking at the instructor positioning and how the instructor may physically, as well as kind of metaphorically, position themselves in a discussion with students, and how that relates to how that discussion goes and how it evolves. So this screenshot illustrates a few specific challenges, like person-over-person occlusion. You can see the teacher standing near this front group is actually covering up a couple of students that are towards the back of the classroom, so we cannot really detect those individuals. But the teacher does move around quite a bit, so later we might be able to detect them. There's also object over person occlusions like desks. You can see in many cases the students are not really visible from the waist down or even higher than that. And there's also some problems not visible in this screenshot necessarily, but with intermittent key point detection, where a person may the tracking may fail for one video frame or two or three in a row, and then be picked right back up. And that can be due to occlusion, but it can also just be due to kind of wavering confidence in the machine learning methods that are used for tracking these key points. Because these are very difficult scenarios. It's not straightforward. Unoccluded people facing the camera, for example. They're moving around, they're covering each other up, they're facing away from the camera, all kinds of stuff like that, which adds quite a bit of noise to the person detection algorithm. There's also some split skeletons. By that I mean in some cases where a person may be detected as two different people because say the head and the shoulders were maybe detected separately and not merged into a single individual person skeleton. So we're trying to grapple with those issues in these very difficult or sort of challenging types of classroom scenarios. So what we're doing with these data is applying OpenPose to do the frame level key point extraction. That gives us results like I showed you in that screenshot. And then doing some person ID assignment and tracking. So trying to figure out who in frame 50 is the same as the skeleton we saw in frame 49, and then trying to track who those people are and assign them IDs throughout the video. So we do that via skeleton alignment scoring, try to come up with a score for how close one person is to another, and then also who the second closest person is. So we use that difference as additional evidence that one person in one frame may be the same person in the previous frame. If the points align pretty well and they are not very close to any other points, then we can be pretty confident it's the same person. But then we also, in addition to just looking one frame in the past, we look through iteratively through several frames in the past, because there can be these situations where students are occluded in the classroom, or where the tracking just sort of randomly fails for a frame or two. And then also trying to combine split skeletons by looking through the past sets of frames to try find places where we have some evidence that those two different people with maybe complementary key points can actually be merged and considered to be one skeleton in the output. And then also interpolating missing skeletons when we have somebody who's missing for just a second or two from the frames. We can try to guess where they were, so that we have a little bit more contiguous tracking of students throughout the classroom, which is important for doing things like identifying who is who in a video, teachers versus students and that type of thing. So in this project, the team includes qualitative analysis exploring many of the same kinds of research questions from a very different methodological approach. And the sort of overarching goal of this project is to explore ways to align these sort of computer vision or AI-driven approaches to pattern discovery in these videos with the manual annotation and the expert analyses that the qualitative team is doing, with the hopes of maybe scaling up the analyses that they can do, as well as informing our analyses and hopefully coming up with some findings that we could not do without this combination of methods. So in the future work on this project, we're working on incorporating audio into these analyses as well, which is not my area of expertise, but a whole new set of AI challenges with the very literally noisy and figuratively noisy from a DSP, digital signal processing kind of perspective. And as well as trying to figure out who is who, teachers versus students in a classroom, maybe trying to do some semi-automated anonymization. So in a lot of these data sets, maybe we don't have permission from everyone to actually analyze their data, and even qualitatively. So it can be really helpful if we can track somebody throughout a video, and we can say in frame 1, okay, this person does not have assent to participate in the research, so we can tag that person, track where they are throughout the video, and then blur them out or otherwise remove them from the video. And then we would also like to apply these unsupervised learning methods that we're looking at, clustering and so on, for the various positions that we see in videos, to try to flag interesting points, whatever interesting means, in long video data, so that the qualitative researchers can then investigate those times in the video to see if that is a better approach than simply watching videos through, to see if that enables qualitative discovery at a faster rate than a computer unassisted approach might. So the second project I want to talk about is a project using the Betty's Brain platform, a learning by teaching platform developed by the Teachable Agents group, Gautam Biswas at Vanderbilt University. And in this software, students construct causal maps, a type of concept map where they link the causes and effects between different topics and processes. In this case, in science courses. So you can see here a screenshot where a student has linked together, for example, deforestation causally reduces vegetation, which absorbs carbon dioxide. And in this environment, the students construct this causal map of how they think the concept they're supposed to be learning works, and then they administer quizzes to a virtual agent named Betty, and then Betty answers those questions according to the causal map that the student has created. So the causal map serves as Betty's brain that Betty uses to answer the questions, and then the students can see which questions Betty got wrong, and thus figure out where their causal map is wrong. So in this study, we collected a bunch of data from students using Betty's Brain, and during this process, we applied real-time affect and behavior detectors, which provided feedback to a couple of interviewers regarding who they should interview. It's a large classroom environment. They can't interview everyone all the time. So we used a mobile app where the interviewers could see, it might now be a good time to interview so-and-so because of a particular learning relevant affective or behavioral event that is occurring. And then in these interviews, students describe their software usage, problem-solving strategies, problems they encountered, etc., with the goal of analyzing these transcripts to discover ways to improve Betty's Brain and to form a better qualitative understanding of how self-regulation operates in this kind of learning by teaching environment. These are audio recorded transcripts. So we applied some good old-fashioned AI methods to measure metacognition from these transcripts. Not an analysis that was originally intended for this project. So we did that first via interview transcription, which was going to happen anyway, but that gets it into a much easier plain text kind of format to work with rather than audio, and then apply some straightforward natural language processing to recognize first-person metacognitive statements. So we're interested in where the student says something about their metacognitive understanding. So an example of this is where a student says something like, "I wouldn't say it surprised me, I already knew it was bad," talking about their causal map, and they go on, but that phrase, "I already knew," is a statement about their knowledge, which is a metacognitive evaluation. And then the interview jumps in and asks a follow-up question, get them to elaborate a little bit, and the student responds, yes, making it make sense when I understand how well reasonably I understand better now. So they're talking again about their understanding, about their awareness of their own thought processes. In contrast, another example from a student is somebody who says, "I've had to reset everything," and the teacher tries to prompt them for more information, or the interviewer rather, and they say, "No, it's not a system problem, it's just that this idiot," talking about Betty, the virtual agent, kept getting everything wrong. An interview follows up, and the student talks about the process that they used for trying to resolve this problem. So they are talking about their problem-solving processes, but without a sort of metacognitive evaluation of what they knew or their understanding. They just knew it was not getting the correct answer, and so they decided to wipe it out and start over. So the NLP method that we used here was actually originally developed for college students, but middle school speech is a bit different, as I'm sure you can imagine. Some differences in vocabulary just due to age differences, as well as the differences in grammar due to speech versus well thought out, edited posts in discussion forums. So we had to adapt the natural language processing method a little bit for these data. We did 3 rounds of iterative tool updates to do this, and 2 rounds of validation. One is a sort of power analysis, and then a final round with a large number of conversational turns where we got relatively decent agreement between a human annotation of these interview transcripts and the NLP method's predictions of metacognitive phrases. So what we found from applying this tool to all these interview transcripts and measuring how student metacognition related to other parts of their experience learning with Betty's brain was that, well, one surprising finding is that the students' verbalized metacognition, normalized per interview, was not actually related to learning, which we expected it would be. However, the interviews themselves were. So the more interviews students did, the better their increase from pre-test to post-test was. So that has some implications for future work in this area, where we may actually want to integrate kind of automated interviews into the Betty's brain system. However, the verbalized metacognition, the count of these kinds of statements per interview did correlate modestly with some metacognitively informed behaviors. So coherent quiz view, for example, what that means is that a student viewed a quiz result in a way that was coherent, or in a way that made sense given their previous actions. And same thing for marking, which is a type of edit that they can make on their causal map. So if they do an action that's informed by their previous action, we consider that to be coherent. That's called coherence analysis. And so, as expected, metacognition did correlate, if modestly, with these kinds of actions, indicating that students who were more aware of of what they knew and what they did not know also engaged in more coherent editing of their causal maps. So in this project in the future, we may explore things like measuring verbalized metacognition in other contexts. This one was interesting and certainly a bit different. And trying to distinguish what we're actually measuring here from other expressions of metacognition, like self-reports, for example. As well as I mentioned, maybe integrating metacognitive reflection via automated interviews into Betty's brain. So those are the 2 projects I wanted to talk about, but just to quickly wrap up, the theme that I'm going for with these projects is of interdisciplinary data reuse. So to give an art example, there's the found object art movement that Marcel Duchamp was famous for, in which his most famous work is this urinal displayed as art in 1917, I believe. And this sometimes, I think, ends up being how we approach data analysis with secondary data, where we take data, at least I have done this in the past, out of the context it was collected in, and from the people who collected it, to answer new research questions. And there's a lot we can learn by doing that, actually. But intentional data, or data that were collected intentionally, which is usually the case, differ in that there's a rich history to these data that we can potentially learn from. So what do the people that collected these data know about these data? And what were their original research questions? And maybe how can we feed back into their research? So in both of these projects, we worked with the people who, and continue to work with the people who collected these data originally for a different purpose, and have come up with different kinds of findings and different kinds of insights than we would have otherwise. Not necessarily better or worse, but different. And that opportunity to explore a new kind of novelty, I think, is very exciting in this classroom data reuse area. So that's all I have for you. Thanks very much for watching this. I'd like to thank my collaborators, and as well as NSF, who provided funding for both of these projects. Thank you.